Hello, this is Dr. Kraus with the second part of the root locus design example videos that I'm doing. You could think of this in two ways, either as a continuation of the previous example in which we're trying to take a PD controller and convert it to a lead compensator. Or you could just think of this as we're starting with some random plant and we're trying to determine whether we need to add a pole or a zero to pass through some desired test point. At either rate, this is our starting transfer function, 6s plus 15 over s squared plus 8s plus 32. And it has poles at a -4 plus 4j and a -4 minus 4j, which you may remember from the previous video. Those are the points that we were trying to place our closed loop poles at. And then we added in a 0 as part of that design for our PD controller, and that was at a -2.5. So part of what we're saying is if we had that plant, it would have a pole here and a pole here and a 0 here. And as part of our next control design problem, my goal is to have the root locus pass through what I think I call S2. Yeah. So let's label this as S2, and S2 is a -8 plus 4j. And so the question is, what would we have to do if this is now our new plant and we're placing this under unity feedback control, just like in the previous example. How do I design this new, I guess I'll call this D2. How do I design D2 to cause the root locus of this system to pass through this desired design point? And just like before, the issue is, as always, how would I'm going to call this L2 now. How would I find the phase of L2 at S2? So I would have a psi from my 0, and then I would have a -phi1 and a -phi2. And so this would be my phi1, and this would be my phi2. So as always with root locus, the issue is how do I make that equal to plus or minus 180, plus or minus n360, whatever. I need the phase of this to go to -180 for this point to be on my root locus. And the question is, would I need to add a pole or a 0, or possibly more than one, or both, to cause the root locus to pass through that point? This is the open loop root locus for our new plant, and the point that we're trying to pass through is like over here somewhere. So again, we're trying to stretch that off to the left, kind of like we were doing before. And I could go through and graphically evaluate all three of these. For example, I know that this one's 180. And this is 1, 2, 3, 4. So phi2 is probably 90 plus the arctan of 4/8. Similar to last time, only I think we had a 3 in the numerator. And then my psi, I would have to do a little bit of math, not a lot. So I guess that's going to be 5.5 on this side and 4 on that side. And so psi would be the inverse tangent of, I think that's 5.5 over 4. So I could find all three of those. However, if I happen to have access to a computer that has a control design module kind of going on, I could define my S2 and I could simply say, evaluate that at that point. And what I mean when I say that is give me a complex number that corresponds to that transfer function evaluated at that point. And then I could take the arctan 2 of my imaginary over my real, and I'd come up with this number. Now, the only risk of doing it this way is it's very possible that this would be off by 360 degrees from what I really mean, but in this case, it's not. So how would I know? If I, based on geometry, kind of roughly expected, say, 150 degrees of phase instead, or sorry, -150, instead got a positive 210 or something, you just have to think about it and double check it. So in this case, at my test point, my plant has a phase of a negative 152.6. So it must be that psi minus phi1 minus phi2 is equal to a negative 152.6. So if I want this test point to be on the root locus, if I want to force the root locus to pass through that point, then I've got to do something. I'm going to add or subtract something. So what do I need to add or subtract to get this to a negative 180? So hopefully it's obvious that I actually need to subtract an additional 28 something. I've done the math over here. Sorry. So I need an additional 27.4 in the negative phase, and so that's actually caused by a pole. So I need what I would call a phi3 to be that. So if I took psi minus phi1 minus phi2 minus phi3, that would now equal a negative 180 degrees. So because this number is above negative 180, I need a pole to cause my target point to be on my root locus. If it were below negative 180, I would need a 0 or a lead compensator to bring my phase up. But this requires a pole. Could also be done with a lag compensator, but we're just going to add a pole to get us to here. And so what we're really saying is that wherever this other pole is, there's a phi3 that's known to be 27.4 degrees. So it's just a question of doing the trigonometry to say, okay, I know this side to be 4, and I know that the tangent of 27.4 is equal to 4 divided by what I call a dx. So this distance is how far my pole needs to be away from my target point to cause that point to be on the root locus. So I've done the math, or Python has done the math for me, and it turns out that dx needs to be 7.7. So if I add that to my original pole location, it turns out that P has to be 15.7. So this is dx, this is 7.7. Sorry, this is 8. Yeah, this distance is 8 from here to here. So my pole is dx plus 8. Okay. So what I think I'm now saying is that my new controller, call this d hat 2, would be 1 over s plus 15.7. I would multiply that by my plant transfer function that's the start of this problem, the PD design, or however you want to think about that. And so I've got a new L that would be 1 over s plus 15.7 times 6s plus 15 divided by s squared plus 8s plus 32. So if I draw, or have Python draw for me, the root locus of this thing, it ought to pass through my test point of negative 8 plus 4j. So here I define the D2, define the L2, double check that at that point, my L2 should have a phase of negative 180, and it does. And then I generate the root locus of that, and we can see that we do, in fact, pass through negative 8 plus 4j. And then if I wanted to know the k that corresponded to that, I use the magnitude condition. And so M2 would be the MP.ABS of L2 evaluated at S2. And so the magnitude of that is 0.1313 apparently. And so the k that puts me there is 1 over that. And then I could again find the closed loop transfer function for this new design, and in fact find that it does have poles at a negative 8 plus or minus 4j. And then there's this additional pole there corresponding to this guy. Oh, sorry. That's a k that goes way too far. So somewhere in here is if I, well, what did we say k was? K stops at 7.62. So if I said 7.62, show me my root locus. So there I am with my root locus stopping exactly at my target point, and then I have this third pole. So again, key idea. If I have a target point and I go in and I evaluate my transfer function at that target point, and if that number is above negative 180 degrees, then I need an additional pole or a lag compensator to pull that down. If instead, as in the previous example, we find that we're below negative 180, then I need a zero or a lead compensator to pull the overall phase up to negative 180 degrees. Hopefully that's helpful. Thanks.